multi-story building, plus the leader will also be much wider than all previous icebreakers.
The harshest places on Earth are not empty. They are hostile, unstable, and actively destructive. Extreme cold that shatters steel, pressure that crushes hulls, heat that warps machinery. Environments where oxygen disappears, radiation rises, ground collapses, or survival time is measured in seconds. Human beings cannot function in these places for long. Yet exploration, science, industry, and rescue continue anyway. The only reason is machinery built to absorb risks humans cannot. This series examines 12 machines designed not for comfort or efficiency, but for endurance. Each one was engineered to operate where failure is expected and assistance is impossible. These are not stories of innovation for convenience. They are stories of engineering pushed to its absolute limits, where the environment dictates the rules and machines either endure or are destroyed. Antarctic icebreaker ships cutting through the coldest ocean on Earth. Antarctic icebreaker ships exist because ordinary vessels cannot survive the Southern Ocean. Around Antarctica, sea ice can exceed 3 meters in thickness. Pressure ridges stack frozen slabs into solid walls, and temperatures routinely fall below -30 degrees Celsius. In these conditions, hull steel becomes brittle, engines lose efficiency, and navigation errors can trap ships for weeks. Icebreakers were developed to solve a single problem: maintaining access to the southern continent despite ice that never truly retreats. The first purpose-built polar icebreakers appeared in the early 20th century, but modern Antarctic operations expanded after the Second World War. By the 1950s, national research programs required year-round resupply of Antarctic stations. Conventional cargo ships failed repeatedly, forcing governments to invest in vessels specifically designed to break ice rather than avoid it. The basic operating principle was simple but demanding. Icebreakers do not cut through ice at speed. They climb onto it and use their weight to fracture it from above. Hull design reflects this mission. Icebreaker bows are rounded and heavily reinforced, allowing the ship to ride up onto ice sheets. High-tensile steel alloys are used to prevent cracking at extreme cold. Internal framing is far stronger than that of commercial ships, increasing weight but preventing catastrophic damage. Propellers and rudders are shielded to survive repeated impacts with ice blocks. Power systems are equally critical. Antarctic icebreakers require sustained torque, not speed. Many modern vessels use diesel-electric propulsion, where engines generate electricity for motors directly connected to propellers. This allows precise control at very low speeds and reduces mechanical shock when propellers strike ice. Some icebreakers also use multiple propellers and bow thrusters to maneuver in compressed ice fields. Real-world operations demonstrate these demands. In 1983, the German research icebreaker Polarstern entered service, designed for continuous Antarctic missions lasting several months. It carries laboratories, workshops, and medical facilities because outside assistance is impossible once deep in the ice. During the austral summer seasons of the 1990s to early 2000s, Polarstern supported long-term climate and oceanographic studies that required repeated penetration of dense pack ice. Icebreakers also face environmental risk. Ice pressure can close behind a ship, trapping it without warning. Visibility is often reduced by snow and fog, while magnetic compasses become unreliable near the pole. Crews operate under strict procedures, relying on radar, satellite navigation, and constant ice observation to avoid becoming immobilized. Beyond transport, icebreakers are logistical lifelines. They deliver fuel, food, construction materials, and personnel to isolated stations. Without them, permanent scientific presence in Antarctica would be impossible. Icebreakers do not eliminate danger. They reduce it to a level that engineering, discipline, and planning can manage. Their success is measured not by speed or elegance, but by their ability to move at all in an ocean designed to stop everything that enters it. Crawler transporters, moving mountains under relentless heat and pressure. Crawler transporters were created to solve a problem no wheeled vehicle could handle, moving the largest rockets ever built without breaking them. At the Kennedy Space Center, launch vehicles must travel several kilometers from assembly buildings to launch pads while remaining perfectly stable. Any structural flex, vibration, or tilt could damage a rocket before it ever leaves the ground. The crawler transporter exists to eliminate that risk. The first crawler transporters were designed and built in 1965 to support the Apollo program. Each machine was constructed by the Marion Power Shovel Company and delivered to NASA as part of preparations for Saturn V launches. Fully loaded, a crawler transporter weighs more than 2,700 metric tons and can carry payloads exceeding 9,000 metric tons. This makes it one of the heaviest land vehicles ever operated. The machine moves on 8-tracked assemblies, each containing dozens of steel shoes designed to distribute weight evenly across the ground. Instead of rubber tires, the crawler relies on massive steel tracks to prevent sinking and to maintain traction under extreme loads. Even with this design, the crawler travels slowly. Its maximum speed with a rocket on board is about 1 kilometer per hour, a deliberate choice to minimize vibration and structural stress. Power comes from diesel-electric systems similar to those used in large locomotives. Diesel engines generate electricity, which drives electric motors connected to each track assembly. This configuration allows precise control at low speeds and ensures that power is evenly distributed. Steering is accomplished by varying speed between tracks, allowing the crawler to turn without twisting its payload. Heat and pressure present constant challenges. In Florida's climate, surface temperatures can exceed 40 degrees Celsius. The crawler's engines, motors, and hydraulic systems must operate reliably under sustained load in these conditions. Bearings, gearboxes, and electrical components are oversized and heavily cooled to prevent failure during multi-hour transports. Stability is the crawler's most critical function. Hydraulic leveling systems keep the platform within a few degrees of level, even when crossing uneven terrain or climbing ramps onto launch pads. During Saturn V operations between 1967 to 1973, this precision was essential. The rockets were tall, narrow, and structurally delicate. A small tilt could cause irreversible damage. After the Apollo era, the crawler transporters were modified to support the Space Shuttle program, which began operational flights in 1981. New platforms and support systems were installed, but the core machines remained the same. They continued operating for decades, accumulating thousands of kilometers under extreme load without catastrophic failure. Crawler transporters are not fast, flexible, or efficient by conventional standards. They are purpose-built machines designed for a single task under extreme conditions. Their success is measured not by speed, but by reliability. Each successful launch begins hours earlier, moving slowly across concrete and gravel, carried by a machine designed to move mountains without being noticed. Deep-sea submersibles, machines that survive, crushing ocean depths. Deep-sea submersibles are built to operate in an environment that is instantly fatal to humans. Below 1,000 meters, sunlight disappears completely, temperatures fall close to freezing, and water pressure increases to levels that will collapse ordinary structures. At depths of 4,000 meters, pressure exceeds 400 atmospheres. Every component of a deep-sea submersible is designed around this single threat: crushing force. Early attempts to reach the deep ocean relied on rigid chambers and tethered systems. A major breakthrough occurred in 1960 when the bathyscaphe Trieste descended to the Challenger Deep in the Mariana Trench. The dive reached nearly 11,000 meters, where pressure exceeded 1,000 atmospheres. The mission proved that extreme depth was survivable with proper engineering, but it also showed how narrow the margin for error was. Any structural failure at that depth would have been instantaneous. Modern deep-sea submersibles rely on pressure resistance rather than pressure avoidance. The core of most crewed submersibles is a spherical pressure hull. Spheres distribute stress evenly, preventing weak points where cracks can form. Materials such as titanium alloys and high-strength steel are used because they retain structural integrity under extreme pressure. Even viewports are carefully engineered, often made from thick acrylic shaped to resist inward collapse. Life support systems are another critical element. Crewed submersibles must carry oxygen supplies, carbon dioxide scrubbers, temperature regulation systems, and emergency reserves. These systems must function reliably for missions lasting 8 to 12 hours or longer. Unlike surface vessels, submersibles cannot be repaired or resupplied during a dive. Any malfunction must be managed internally until recovery. Scientific deep-sea exploration expanded significantly during the 1960s and 1970s. One of the most important vehicles was DSV Alvin, launched in 1964. Alvin enabled repeated deep dives and direct human observation of the seafloor. In 1977, it played a central role in the discovery of hydrothermal vents along the Galapagos Rift. These vents supported ecosystems based on chemical energy rather than sunlight, fundamentally changing scientific understanding of life on Earth. Navigation at depth presents additional challenges. GPS signals do not penetrate seawater, forcing submersibles to rely on inertial navigation systems, sonar mapping, and acoustic positioning from surface ships. Communication is limited to low-bandwidth acoustic signals, often delayed and unreliable. Pilots operate with restricted visibility, depending on external lights and cameras to see only a few meters ahead. By the late 20th century, remotely operated vehicles expanded deep-sea access, allowing exploration without risking human crews. However, crewed submersibles remain essential for tasks requiring complex judgment, fine manipulation, and direct visual assessment. Both types of vehicles depend on the same principles: redundancy, structural integrity, and conservative engineering. Deep-sea submersibles do not overcome the ocean through force. They survive by respecting physical limits. Every dive is governed by pressure calculations, material tolerances, and strict operational discipline. In the deepest parts of the ocean, survival is not a matter of strength or speed, but of engineering precision. Mars rovers. Engineering built to operate without human help. Mars rovers are designed to function in complete isolation, millions of kilometers from human support. On the surface of Mars, temperatures swing from -100 degrees Celsius at night to near zero during the day. Dust storms can last for weeks. Solar radiation is unfiltered by a thick atmosphere, and communication with Earth is delayed by several minutes each way. In this environment, real-time control is impossible. Every rover must think, diagnose, and survive largely on its own. The first successful Mars rover was Sojourner, which landed in 1997 as part of the Pathfinder mission. Sojourner was small and short-lived, but it proved that mobile robotic exploration on Mars was possible. It operated for 83 days, far beyond its planned mission, while transmitting critical data about Martian soil and terrain. Its success laid the groundwork for far more ambitious designs. Mars rover engineering is dominated by autonomy. Commands sent from Earth can take between 4 to 20 minutes to arrive, depending on planetary alignment. By the time instructions are received, conditions may have changed. To compensate, rovers use onboard hazard detection, navigation cameras, and software that allows them to plan safe routes, avoid obstacles, and stop if danger is detected. This autonomy prevents damage that would otherwise end missions instantly. Power systems reflect long-term survival needs. Early rovers relied on solar panels, but dust accumulation posed a constant threat. The rovers, Spirit and Opportunity, were designed for 90-day missions but survived for years. Opportunity operated until 2018, when a planet-wide dust storm blocked sunlight and ended communications. Its longevity demonstrated both robust engineering and the unpredictable risks of Mars. Later, rovers shifted to nuclear power. Curiosity, which landed in 2012, uses a radioisotope thermoelectric generator. This system converts heat from radioactive decay into electricity, providing continuous power regardless of dust or sunlight. The design allows Curiosity to operate complex instruments, drill into rock, and function through harsh Martian winters. Mechanical durability is another challenge. Rovers must traverse sharp rocks, sand traps, and slopes without repair. Wheels are designed to flex under load while resisting fracture. Redundant motors and joints ensure that failure in one component does not end the mission. Software monitors system health continuously, adjusting operations to preserve function. In 2021, Perseverance introduced advanced autonomy and sample caching systems. It is tasked with collecting rock samples for future return to Earth. Perseverance also deployed the Ingenuity helicopter, demonstrating powered flight in the thin Martian atmosphere. Mars rovers are not remote-controlled vehicles. They are independent explorers built to survive without rescue, repair, or replacement. Every design choice assumes isolation, delay, and failure as normal conditions. Their success is measured not by speed, but by how long they continue operating in an environment where help will never arrive. Arctic oil drilling rigs, machinery that works below freezing point. Arctic oil drilling rigs are built to operate where standard industrial equipment fails almost immediately. In regions above the Arctic Circle, temperatures regularly fall below -40 degrees Celsius. Winds exceed hurricane strength, and sea ice exerts constant pressure on any structure left exposed. Machinery must function through months of darkness, isolation, and cold, intense enough to crack steel and freeze unprotected systems solid. Modern Arctic drilling expanded during the Cold War era, when major oil discoveries were confirmed in Alaska and northern Russia. In 1968, commercial oil was discovered at Prudhoe Bay in northern Alaska, triggering the development of large-scale Arctic extraction. Engineers quickly learned that conventional rigs designed for temperate climates could not survive Arctic conditions. Equipment failures, frozen fluids, and structural damage were common during early operations. Cold dictates every design decision. Steel becomes brittle at extreme low temperatures, increasing the risk of sudden fracture. Arctic rigs use specially formulated low-temperature steels and reinforced joints to prevent cracking. Mechanical systems are enclosed within insulated modules to retain heat. Critical components such as valves, pumps, and control systems are heated continuously to remain operational. Drilling fluids present another challenge. Mud used to stabilize wells and remove cuttings can freeze or thicken in extreme cold. Arctic rigs rely on heated circulation systems and chemical additives to maintain fluid performance. Any interruption in circulation risks freezing inside pipes, which can halt operations entirely and damage equipment beyond repair. Ice is a constant threat for offshore Arctic rigs. Sea ice can exert enormous horizontal pressure, capable of deforming platforms or severing support structures. To counter this, some rigs are built on gravity-based structures with sloped sides designed to deflect ice downward. Others use artificial islands made of gravel and ice, rebuilt each season to support drilling equipment. Logistics compound the difficulty. Arctic drilling sites are often accessible only a few months per year. During winter, aircraft and ice roads become the primary supply routes. Equipment, fuel, and food must be stockpiled in advance because resupply during storms or polar night may be impossible. Any miscalculation can shut down operations for months. Human factors also influence design. Crews live and work in confined facilities designed to protect against cold and isolation. Living quarters are heavily insulated, pressurized, and connected by enclosed walkways to prevent exposure. Even routine maintenance must be planned carefully, as tools and protective gear become difficult to handle in extreme cold. Environmental risk adds further constraints. Oil spills in Arctic conditions are exceptionally difficult to contain or clean. Ice, darkness, and remoteness limit response options. As a result, Arctic rigs incorporate multiple containment systems, redundant valves, and constant monitoring to reduce failure probability. Arctic oil drilling rigs do not defeat the environment. They endure it by limiting exposure and controlling variables wherever possible. Their success depends on preparation, redundancy, and conservative engineering. In a region where mistakes cannot be corrected quickly, survival is measured not by output, but by the ability to keep operating at all below freezing point. High-altitude mining trucks, operating where oxygen nearly disappears. High-altitude mining trucks are designed to work in environments where human endurance and standard machinery rapidly fail. In mining regions such as the Andes and the Tibetan Plateau, operations commonly take place above 4,000 meters. At these elevations, oxygen levels drop by roughly 40%, temperatures fluctuate sharply, and steep terrain places constant strain on engines, brakes, and structural components. Moving hundreds of tons of material under these conditions requires engineering that compensates for air, gravity, and isolation. The expansion of high-altitude mining accelerated during the late 20th century as demand for copper, lithium, and precious metals increased. Major open-pit mines in Chile and Peru began operating at elevations previously considered impractical. Traditional haul trucks suffered severe power loss because internal combustion engines depend on oxygen for efficient combustion. At altitude, reduced air density leads to incomplete combustion, overheating, and reduced output. To address this, manufacturers redesigned engines specifically for thin air. Turbocharging became essential. Turbochargers compress incoming air, increasing oxygen availability inside the engine. At high altitude, multi-stage turbo systems are often used to maintain power levels closer to sea level performance. Even with these adaptations, engines must be derated, meaning maximum payload and speed are reduced to preserve reliability. Cooling systems face similar challenges. Thin air removes heat less effectively, increasing the risk of engine and brake overheating. High-altitude mining trucks use oversized radiators, enhanced airflow channels, and advanced cooling fluids to manage temperature. Braking systems are also reinforced, as long downhill hauls generate extreme heat that can lead to brake fade or failure. Electric retarder systems are commonly used to slow trucks without relying solely on friction brakes. Fuel efficiency and emissions control become more complex at altitude. Engines must balance power output with stable combustion despite reduced oxygen. Electronic engine management systems constantly adjust fuel injection timing and air mixtures to prevent knocking or stalling. These systems rely on sensors that monitor pressure, temperature, and load in real time. Human operators face physical stress as well. Hypoxia, fatigue, and reduced reaction time are common at high altitude. To mitigate this, modern mining trucks feature pressurized and climate-controlled cabs that maintain oxygen levels closer to those at lower elevations. Shift schedules are adjusted, and crews undergo acclimatization programs to reduce health risks. Logistics amplify the difficulty. High-altitude mines are remote, often accessible only by narrow mountain roads. Replacement parts, fuel, and maintenance crews must be transported over long distances. Downtime is costly, so trucks are built with redundancy and modular components that allow faster repairs on site. High-altitude mining trucks are not optimized for speed or comfort. They are optimized for survival and consistency in an environment that degrades both humans and machines. Their success is measured by reliability rather than raw performance. In places where oxygen is scarce and mistakes are amplified, these trucks keep moving by compensating for every limit imposed by elevation rather than attempting to ignore it. Nuclear icebreaker reactors. Power systems built for eternal winter. Nuclear icebreaker reactors were developed to solve a problem no conventional engine could overcome. In polar seas, diesel-powered ships lose efficiency, fuel freezes, and refueling becomes nearly impossible during long winters. Ice thicker than 3 meters can trap vessels for months. To operate year-round in these conditions, icebreakers required a power source that could deliver massive, continuous energy without relying on fuel resupply. Nuclear reactors provided that solution. The concept became reality in the Soviet Union during the Cold War. In 1959, the nuclear-powered icebreaker Lenin entered service, becoming the first surface ship in the world driven by nuclear reactors. Its mission was to keep Arctic shipping lanes open along the northern sea route, a passage critical for transporting resources between Europe and Asia. Conventional icebreakers could not maintain these routes through winter. Nuclear power changed that calculation. Reactor design for icebreakers prioritizes reliability and endurance over speed. Unlike reactors used for electricity generation, icebreaker reactors are compact and heavily shielded. Designed to fit within reinforced hulls, they generate heat to produce steam, which drives turbines connected to electric motors. These motors deliver immense torque to propellers, allowing ships to crush ice rather than slice through it. Operating conditions are extreme. External temperatures can fall below -50 degrees Celsius, while seawater freezes instantly on exposed surfaces. Reactor systems must remain stable despite violent hull vibrations caused by ramming ice repeatedly. Cooling systems are engineered to function in freezing seawater without clogging or losing efficiency. Redundant safety systems ensure that reactor stability is maintained even if surrounding mechanical systems fail. Fuel endurance is the decisive advantage. A nuclear icebreaker can operate for years without refueling, compared to weeks or months for diesel vessels. This capability allows uninterrupted missions during polar night, when darkness lasts for months and resupply is impossible. It also enables icebreakers to escort convoys through remote regions without returning to port. Crew safety and containment are critical concerns. Icebreaker reactors are enclosed within multiple layers of shielding to limit radiation exposure. Crews undergo specialized training, and reactor compartments are isolated from living quarters. Monitoring systems operate continuously to detect pressure changes, temperature anomalies, or radiation leaks. Safety protocols are designed for environments where external assistance may be days or weeks away. Nuclear icebreakers also face political and environmental scrutiny. Accidents in polar regions would be difficult to manage, and radioactive contamination would persist for decades. As a result, reactor designs emphasize conservative operating limits and fail-safe shutdown mechanisms. Despite these risks, nuclear icebreakers remain in service because no alternative power system can match their endurance. These reactors are not symbols of excess, they are solutions to geographic reality. In regions defined by ice, darkness, and isolation, nuclear icebreaker reactors provide the only reliable means of sustained operation. Their success lies not in dominance over nature, but in continuous function where winter never truly ends. Tunnel boring machines, digging through rock, water, and collapse zones. Tunnel boring machines, commonly known as TBMS, are built to operate in environments where collapse, flooding, and crushing pressure are constant threats. Underground conditions vary dramatically within short distances. Solid rock can suddenly give way to loose soil, pressurized water, or fractured fault zones. TBMs must continue advancing through all of it without stopping, because halting progress underground can be more dangerous than moving forward. The modern TBM emerged in the mid-20th century as cities expanded and surface space disappeared. Early tunneling relied on drilling, blasting, and manual excavation, which caused frequent cave-ins and severe worker casualties. Large infrastructure projects demanded safer and more predictable methods. TBMS replaced explosive force with continuous mechanical excavation, allowing tunnels to be built beneath cities, rivers, and mountains with greater control. TBMs are massive machines, often exceeding 100 meters in length and weighing thousands of tons. At the front is a rotating cutter head fitted with hardened steel or tungsten cutters. These cutters grind through rock or soil, while hydraulic systems push the machine forward. As material is excavated, it is transported backward through conveyors or slurry pipelines for removal. Different ground conditions require different TBM designs. Hard rock machines are built to crush solid stone, while earth pressure balance and slurry shield machines are used in soft, water-saturated ground. In unstable zones, TBMS maintain constant pressure at the tunnel face to prevent collapse or sudden inflow of water. Sensors monitor ground behavior in real time, adjusting pressure and speed automatically. Water presents one of the greatest risks. Tunneling beneath rivers or seabeds exposes machines to extreme hydrostatic pressure. A failure at the tunnel face can result in rapid flooding. To prevent this, TBMS use pressurized chambers and sealed bulkheads. Crews perform maintenance inside pressurized environments similar to deep-sea diving, where decompression procedures are required to avoid injury. Structural support is installed as the TBM advances. Precast concrete segments are placed behind the cutter head to form a rigid tunnel lining. This process stabilizes the ground immediately, preventing deformation or collapse. The speed of excavation and lining installation must remain synchronized. Any delay can compromise tunnel integrity. Mechanical stress is constant. Cutter heads wear down rapidly, especially in abrasive rock. Replacing cutters requires stopping the machine and, in some cases, entering high-pressure zones. Downtime is costly and risky, so TBMS are designed for durability and redundancy. Backup systems ensure that failure in one component does not halt progress entirely. Tunnel boring machines do not conquer the underground, they negotiate with it. Their success depends on continuous movement, constant monitoring, and precise control. In environments where gravity, water, and geology are always working against stability, TBMS survive by advancing steadily through conditions that would otherwise collapse without warning. Desert pipeline crawlers, machines built for heat that melts steel. Desert pipeline crawlers are designed to operate in some of the most punishing surface conditions on Earth. In major desert regions such as the Middle East, North Africa, and Central Asia, ground temperatures can exceed 70 degrees Celsius, while ambient air regularly rises above 50 degrees. Sand infiltrates every moving component. Solar radiation degrades materials, and long distances separate work sites from maintenance support. These machines exist to move, weld, inspect, and maintain pipelines where human labor alone cannot survive for long. Large-scale desert pipeline construction expanded rapidly after the Second World War, as oil and gas infrastructure pushed across arid regions. Pipelines stretched hundreds or thousands of kilometers, often far from roads, water, or settlements. Manual transport of pipe sections was slow and dangerous. Crawlers were developed to lift, align, and move massive steel pipes continuously across unstable sand and rock. Heat defines the engineering limits. Steel weakens as temperatures rise, lubricants thin, and electronic systems overheat. Desert pipeline crawlers use heat-resistant alloys, reinforced frames, and thermal shielding to protect critical systems. Engines are derated to prevent overheating, sacrificing speed for survival. Cooling systems are oversized, with multiple radiators and high-flow fans designed to operate even when air provides minimal cooling benefit. Mobility across sand is another challenge. Narrow tracks or wheels sink quickly, immobilizing heavy machines. Crawlers use wide tracks with low ground pressure to distribute weight evenly. Suspension systems are simplified and reinforced to resist sand abrasion. Seals and filters are layered to keep fine dust out of engines, hydraulics, and control systems. Without constant filtration, engines can fail within hours. Pipeline alignment requires precision despite heat distortion. Steel pipes expand significantly under desert sun, altering length and shape throughout the day. Crawlers are equipped with adjustable clamps and positioning systems that compensate for thermal expansion. Welding operations are often scheduled during night hours to reduce temperature stress and improve joint integrity. Autonomy and reliability are critical. Desert pipeline routes often lack immediate mechanical support. Breakdowns can halt entire construction schedules and expose crews to dangerous conditions. Crawlers are designed with redundant hydraulic circuits, backup power systems, and simplified repair access. Components are modular, allowing rapid replacement without specialized tools. Human operators face extreme risk. Cabins are sealed, air-conditioned, and insulated to protect against heat exhaustion. Even so, shifts are tightly controlled and crews rotate frequently. Heat illness remains a constant concern. Machines carry water, emergency supplies, and communication systems because rescue may be hours or days away. Environmental exposure also accelerates wear. Sandstorms erode surfaces and obscure visibility. Electronics must function despite vibration, heat cycling, and contamination. Control systems are hardened and shielded to prevent failure under constant stress. Desert pipeline crawlers are not optimized for comfort or efficiency. They are optimized to function where failure is expected. Their purpose is simple and unforgiving. Keep pipelines moving forward in environments where steel softens, humans weaken, and stopping work can mean abandoning entire projects. Volcanic monitoring robots. Entering zones. Humans cannot survive. Volcanic monitoring robots are built to operate in environments where human survival is measured in seconds. Active volcanoes expose equipment to extreme heat, toxic gases, unstable ground, and sudden explosive events. Temperatures near lava flows can exceed 1,000 degrees Celsius, while acidic gases corrode metal and electronics. These conditions make direct human observation impossible during eruptions. forcing scientists to rely on machines that can enter zones no person safely can. The development of volcanic robots accelerated in the late 20th century as monitoring shifted from distant observation to direct data collection. Early volcanology relied on visual surveys, seismic readings, and gas samples collected at great risk. Fatal accidents during eruptions highlighted the need for remote systems. Robots were designed to approach craters, lava domes, and vents while transmitting real-time data back to researchers. Heat resistance is the primary engineering challenge. Standard electronics fail quickly at high temperatures. Volcanic robots use heat shielding, ceramic insulation, and reflective coatings to delay thermal damage. Internal components are isolated within cooled compartments, often using passive cooling because active systems can fail under ash and debris. Operational time near lava is limited, so missions are carefully planned to extract maximum data before systems degrade. Mobility is another obstacle. Volcanic terrain is unpredictable, consisting of loose ash, sharp rock, hardened lava, and collapsing ground. Robots are equipped with tracked systems, articulated legs, or reinforced wheels to maintain stability. Some designs prioritize low profiles to reduce exposure to falling debris. Others use tethered systems that allow retrieval if mobility fails. Gas exposure poses constant risk. Volcanic plumes contain sulfur dioxide, carbon dioxide, hydrogen sulfide, and other toxic compounds. Sensors must operate accurately despite corrosive environments. Robots carry gas analyzers, thermal cameras, and spectrometers to measure emissions directly at the source. These readings help predict eruption behavior and assess danger levels for nearby populations. Communication reliability is critical. Ash clouds and rugged terrain interfere with radio signals. Robots often operate with relay stations or autonomous data storage if signals are lost. Navigation systems combine GPS, inertial sensors, and visual mapping to function when satellite signals degrade near steep volcanic structures. In the 2000s, robots were deployed at active sites such as Mount Etna and Kilauea to collect close-range thermal and gas data. These missions demonstrated that robotic systems could survive long enough to provide information unavailable through remote sensing alone. Data gathered improved eruption forecasting and evacuation planning. Volcanic robots are considered expendable by design. Engineers accept that some missions will end in destruction. The goal is not machine survival, but data recovery before failure. Redundancy is built into sensors and memory systems to preserve information even if movement stops. These machines do not neutralize volcanic danger. They allow limited access to it. By entering lethal zones briefly and remotely, volcanic monitoring robots extend human understanding without direct exposure. Their value lies in reaching places where human presence would mean certain injury or death, transforming impossible observation into actionable knowledge. Space Station Life Support Systems. Machines that keep humans alive in vacuum. Space Station. Life support systems are designed to sustain human life in an environment that is instantly fatal. In orbit, there is no air, no atmospheric pressure, extreme temperature variation, and constant exposure to radiation. A single system failure can lead to loss of consciousness within seconds and death shortly after. Survival depends entirely on machines that create a controlled, artificial environment inside a structure surrounded by vacuum. Human spaceflight required closed-loop life support from its earliest days, but long-duration missions made these systems far more complex. Short missions could rely on stored oxygen and water. Space stations, however, required continuous recycling. Systems had to operate for months or years with no possibility of rapid resupply. Every kilogram launched into orbit carried extreme cost, making efficiency a necessity rather than a preference. Air management is the most critical function. Life support systems generate oxygen, remove carbon dioxide, and regulate pressure. Oxygen is produced through electrolysis, splitting water into hydrogen and oxygen. Carbon dioxide is removed using chemical scrubbers or regenerative filters. If carbon dioxide accumulates, crew members experience headaches, confusion, and eventually loss of consciousness. These systems must operate continuously without interruption. Water recycling is equally vital. Space stations recover water from humidity, condensation, and even urine. Filtration systems remove contaminants and microbes, producing potable water that meets strict safety standards. Without recycling, stored water would be exhausted quickly. Any failure forces rationing and threatens mission continuation. Temperature and humidity control prevent lethal extremes. In sunlight, external temperatures can exceed 100 degrees Celsius. In shadow, they can fall below -100. Thermal control systems use radiators, heat exchangers, and fluid loops to move excess heat away from living spaces. Humidity is carefully managed to prevent condensation, corrosion, and microbial growth. Radiation exposure presents an ongoing threat. Life support systems work alongside structural shielding to limit exposure, but monitoring is constant. Solar storms can increase radiation levels dramatically. In such events, crews shelter in more protected modules while systems maintain airflow and pressure under abnormal conditions. Redundancy defines every design decision. Critical components have backups, often multiple layers deep. Systems are isolated so failures do not cascade. Crews are trained to perform repairs using onboard tools and spare parts. Maintenance is constant because replacement from Earth can take months. Human waste management is integrated into life support. Waste must be contained, processed, and stored safely without contaminating air or water systems. Failure introduces biological hazards that compromise the entire station environment. Life support systems do not create comfort. They create survivability. Every breath, every sip of water, and every stable temperature reading depends on machines operating without pause. In orbit, there is no margin for error, no external rescue, and no natural environment to fall back on. These systems keep humans alive not by overcoming space, but by isolating crews completely from it, one controlled process at a time. Disaster response robots, operating where Earth has already failed. Disaster response robots are deployed when environments become immediately lethal to humans. Earthquakes, nuclear accidents, chemical explosions, and building collapses create conditions defined by unstable structures, toxic air, extreme heat, and unpredictable aftershocks. In these zones, sending human responders first can result in additional casualties. Robots are designed to enter before people, providing visibility, data, and limited intervention where survival time for humans is measured in minutes. The need for disaster robots became clear during late 20th century industrial and natural